We built a working simulator of Chernobyl SKALA computer.
You can enter request codes, retrieve values, check warning and emergency set points, launch programs, and much more. So, today we will show you how to perform here different operations used to monitor a nuclear reactor, just as real operators did back in the day. But first, I have some news about the entire project. Our reactor control panel, SKALA status display, and several of our other large creations are now installed at the Zona Art Museum. It is located inside the office of the Chornobyl Nuclear Power Plant in Slavutich. They all work, but our goal was never to build panels that simply blink beautifully. We want all of them to work together as one system, and for that they need a certain brain. And just as at a real reactor unit, that brain will be SKALA. And here I also want to express our enormous thanks to the experts from the Chornobyl Nuclear Power Plant. They worked with this technology back in the day, and they shared so many important details with us, so thank you once more. But as you know, I love to go big. So the next thing we are currently building is a replica of one of the reactor-channel mnemonic displays, the so-called MTK. Ours will be slightly scaled down, but still complete. So remember to subscribe if you do not want to miss it. And as always, progress updates and bonus materials will be also posted on our Patreon page. The link is in the description below. Okay, let's do some action. So, we have two keyboards, officially called request devices. Every reactor operator had one, and the engineers responsible for SKALA itself also had the same, but in another hole. We built ours in this engineering configuration with these extra switches, because it simply takes up less space. The keyboard on the right is used to enter numbers, work with MTKs and launch subprograms. The keyboard on the left is used to request and retrieve an enormous range of parameters of all systems of the reactor unit. There are thousands of them, and each has own code consisting of 2 letters and 5 digits. But as you may remember, SKALA does not have traditional computer monitors. And instead, its answers appear on indicator assemblies called display sets. We have two, the first set and the second set. Alright, let us begin with something simple. So, the code I have just entered requests the electrical output of the entire power unit. The lower display shows the request code, and the upper one shows the answer, it is 1000 megawatts. The middle display normally shows the deviation from the nearest permitted limit, so-called setpoint. Well, I didn't define one for this particular code, so the display shows a status code 0000. I can place another parameter on the second display set, and this one shows the electrical output of one of 2 turbine generators. And here it is, 505 megawatts. And in the same way we can examine much smaller parts of the reactor unit. For example, this code gives the oil temperature in a very specific bearing of the chosen turbine generator. And there are codes like this for almost everything. And at this point you may be thinking, but this is insane, yeah, there are tens of thousands of these codes, how anyone could actually remember all that? Well, it's right, there are thousands of them. But all of them always follow a common logic. Operators didn't need to memorize every existing combination, they needed before all to understand the language behind it. Let me show you in detail. So, to enter a request you press one button in each column. The code is built in a sense from something very broad to something extremely specific. It's like a funnel. I will use the reactor's thermal power as an example. The first column, containing Cyrillic letters, identifies a major system or big group of parameters. For example, A represents the reactor as a whole. T, as you already saw, represents the turbine. Then M refers to the turbine mechanical systems. N represents pumps, and so on. But thermal power is associated with steam generation. And so we select the Cyrillic letter P. The second column identifies a large part or subdivision of the system. But we are interested in the system as a whole, so here we select 0. The third column specifies what we actually want to know. We want power, which is represented by the Latin letter N. And the final 4 digits for individual parameters define a particular component or its location inside the system. As we want the total value for the entire system, the address is simply 4 zeros. Next, I select the type of the result using this group of buttons. This one, marked PRM, which comes from parameter, means that we want to retrieve the parameter value itself. Then I press measurement and use one of these two switches to send the answer to either the first or the second display set. And here is our answer, 3200 megawatts of thermal power. This is the normal value when the RBMK 1000 reactor is operating in its normal power generation mode. However, this time here we have not 4 zeros, but some another number with a strange symbol in front of it. That's important thing. The number is the deviation from the nearest set point, shown in percents. And the symbol tells us that our current power is still below that set point. But what exactly is a set point? Well, put simply, it's a threshold that the parameter should not cross. Reaching one may trigger a warning or automatic power reduction, but in more serious cases it can trigger emergency protection. Some parameters have all 4 main types of set points, others have only 1 or 2, and some have no set points at all because they may not have sense. In our thermal power example, the display tells us how much margin remains before we reach the warning high set point. But we see percents, which is actually useful, and still, what is the actual numeric value these percents accounted from? There is a function for that. So below the keyboard we have 4 buttons used specifically for working with set points. I leave our request code unchanged as P0N for zeros, but then I select PP, which means warning high set point, and send it to the second display set. The result is 3264 megawatts. That's exactly 2% above the nominal power. When this value is reached, an alarm will activate. But I also programmed a more extreme value representing a condition that is already no longer permitted. I select AP, which is emergency high set point, and the result is 3520 megawatts. At this power level in the real reactor unit there won't be any warnings, there will activate the emergency protection by reactor power. But what happens if I request a set point that does not exist? For example, I didn't add an emergency low power for this parameter. In that case, SKALA displays error code 303, which means non-existent set point. There are actually around 10 error codes of this kind. For example, if I enter a request code that doesn't exist at all, I receive error code 301. For convenience, some codes were sometimes written directly onto mnemonic displays. For example, you may remember this mnemonic panel we built last year, and its upper section mainly represents various gas systems used to monitor conditions of reactor integrity. On the real panel at the Chornobyl Nuclear Power Plant, on that panel there are those stickers next to the word graphite. Let's enter one of them. As a reminder, the letter A in the beginning tells us that we are monitoring the reactor as a whole system. And the result is the graphite temperature in the corresponding part of the core, 490 degrees Celsius. Well, I programmed this particular value as an example, because the actual temperature would vary depending on the location inside the core and the reactor's operating mode. This graphite must be constantly cooled down, so for this, through the gaps between graphite blocks circulates a dry nitrogen-helium mixture. But besides cooling, it also plays another important role. It helps detect leaking reactor channels. Basically, if a pressure tube develops a crack, coolant can escape into the surrounding reactor space. The gas then becomes humid, sensors located above the core detect that moisture and then warn the operator that the channel may have ruptured. For example, we can check how much of this gas is being supplied inside the reactor space. The request is ROG 4211. This letter G represents flow rate. The answer, 800 cubic meters per hour. And then we, for example, can check the pressure at which this mixture is supplied. For pressure, we replace G with P for pressure. And the result is 150 millimeters of water column. Well, here I need to note, some pressure values can be shown in these units, some in pascals, some in kilograms of force per square centimeter. It normally depends on the system and how big the value is. Another code, A0P4311, gives us the pressure of the same mixture when it exits from the reactor space. It is lower, approximately 50 millimeters of water column. But everything we have looked at so far have been so-called parameters of individual monitoring. But this is where SKALA can do even more interesting things, because it can also work with channel-by-channel data. An RBMK reactor contains almost 2000 channels. Most of them contain nuclear fuel. Others contain control and protection rods, instrumentation or other systems. So using this console, you can retrieve a huge number of parameters for them, either for all channels at once or for one specific channel you are interested in. You choose it using its octal coordinates. These are those numbers written inside the squares. All channel-by-channel request codes begin with the letter K. And the difference is that when we request information about one specific channel, the final 4 digits of the code are its coordinates. And so, let me show you. You surely remember this famous display containing cell-scene indicators that show the position of the control and protection rods. But the same position you can actually retrieve through SKALA. And for this we enter K0S followed by the coordinates of the requested channel. And the display tells us that this particular rod is inserted to a depth of 2.5 meters, measured from its upper limit switch, that is a 0 position. In general, this S usually represents position, although there are some exceptions. For example, entering K0S and 4 zeros gives us one of the reactor's most important parameters. That is the operational reactivity margin, or ORM. It's basically a special number that tells the operator how controllable the reactor is. SKALA calculates the combined effect of all the control rods currently inside the core, and then it expresses it as an equivalent number of fully inserted manual control rods. A normal value is approximately 45 to 48 rods. If the number falls, it means that more rods have been withdrawn and the reactor has less control reserve remaining. So the warning set point is 43 rods, and if the margin falls to 30 rods, continued operation is no longer permitted. In this case, reactor must be shut down. And speaking about controlling a nuclear reaction, it's important to remember one thing. What is happening inside the reactor is pretty much uneven. I would say you can imagine it as a complex three-dimensional wave of energy, and its shape and intensity can be very different in different parts of the reactor core. So you may ask a logical question: how can the operator see what is happening down there? The core contains a large number of sensors, which are called decay detectors, and their positions are marked on the same cell-scene display. SKALA contains an entire group of requests that read them, and this way you can see how unevenly the reaction is developing across the core. Many of the results are expressed as dimensionless coefficients. And to be short for now, the result should be somewhere close to 1.15, 1.35, depending on what exactly we are measuring. The further it moves from 1, the more uneven the energy is distributed inside the active zone. Working with these decay detectors is such a large subject that I guess it deserves its own episode, so I think later we'll make one. One reason the reaction is uneven is that fuel channels operate under very different conditions, depending on where they are located. Their power is generally lower near the edges of the core and it's higher around the central region. But in the very center it's more moderate, because a large number of control rods are concentrated there. And operators told me that in real-life situation, because of that, they often kept two very important requests constantly displayed while the reactor was operating on its normal power. The first one is K5N 4 zeros. It displays the highest power currently registered among all fuel channels inside the core. And at the moment our maximum value is 2.85 megawatts. The warning high set point for a single channel is 2.93 megawatts, and the absolute upper limit is 3 megawatts. If the value reaches the 3 MW, the system will not ask the operator to pay attention using some alarms. Instead, emergency protection will be activated, because it's simply unsafe to work under these conditions. The second important request is K4N for zeros. It shows the minimal margin before a boiling crisis among the all fuel channels. What exactly is that boiling crisis? So, the fuel is cooled by water flowing continuously through the pressure tubes. And at the outlet of the channel, the coolant is already a mixture of water and steam. Under normal conditions, steam makes approximately 14.5% of this mixture by mass. If channel power rises, more steam is produced. And if conditions become too severe, separate steam bubbles begin to merge in a continuous layer around the fuel element surfaces, and that is a big problem. That's because steam transfers heat far less effectively than liquid water. And basically, once this insulating layer forms, the water can no longer remove enough heat. That can make fuel temperature rise extremely quickly, and fuel can just melt. So this number therefore tells the operator how much margin remains before such a condition may begin. The value must remain greater than 1. Yet just controlling power alone is not enough to keep the fuel safe. The coolant must also flow through the channels continuously and at the correct rate. The enormous system responsible for this is called Multiple Forced Circulation Circuit, or shorter KMPC. It consists of 2 symmetrical loops, the left side and the right side. We can use SKALA to check the total water flow through the entire circuit, and by now you can probably guess the request code. What's interesting, when the request is processed, SKALA first displays the number of channels included in the calculation. And then we get the answer: 48,000 cubic meters of water per hour. We also can check the same for left and right sides separately, so the code remains the same, except that instead of 0 we select either 1 or 2. That's always like this: whenever a system has a left and right side, SKALA often uses the digits 1 and 2 in this way. So each side gives us approximately 24,000 cubic meters per hour. And in the same way I can retrieve the flow through one individual fuel channel. In this case, the final 4 digits are replaced with coordinates of that chosen channel. And the result here is 42 cubic meters per hour. And at this point you may have a perfectly reasonable question. I enter the coordinates of a channel and receive some normal value. But if one channel among hundreds develops a dangerous condition, how does the operator actually know which one to check? And this question brings us to this second keyboard, and using it you can do some magic. Here the operator can launch programs that compare the data from detectors with given condition. And every channel matching that condition then lights up on this enormous mnemonic display. Well, in reality this keyboard can perform many different operations, far too many for one single episode. So we will show it all after when we finish our own mnemonic display. And for now I will demonstrate one important example: monitoring reductions in coolant flow. And operators actually told me that this program ran almost constantly on one of those MTK displays. So how do we launch it? On the left keyboard I press only the M button, which means scale measurement. And I do not select anything else here. But on the right keyboard I select program number 4 or program number 8. That depends on which mnemonic display I want to present our data. And then I enter the subprogram number 0 plus 3 zeros 1 and press start. The result will look something like this. The illuminated squares indicate channels where coolant flow is too low. Using coordinates we now can select one of the highlighted channels and investigate it. This is very much real-life situation, so first I request its coolant flow. The result is lower than normal, but this reduced flow alone doesn't tell us how dangerous the situation is. And so the operator needs to check several related parameters. K0K gives us the boiling crisis margin for that particular channel. Here the rule is the same: the result must remain greater than 1. A value of 1.25 is normal, and at 1.03 the alarm will activate. Or we can retrieve the power of this channel in megawatts. And by analyzing these parameters the operator can then understand what action is actually needed. There are some other channel-by-channel requests. For example, we can retrieve the temperature of the nitrogen-helium mixture around that particular channel. This is the same gas system we discussed earlier when we talked about this mnemonic panel. The request starts with code, followed with the channel coordinates, and the resulting temperature is normally between approximately 30 to 35 degrees Celsius. And what is interesting is that this value changes with the seasons, and so does the set point. In summer it's approximately 48 degrees, and in winter it's closer to 40. So earlier we used this keyboard to enter a subprogram number, but for other operations it can be also used to enter numeric values. In this case, these black buttons enter the main digits, and the red buttons specify the decimal exponent. In practical terms, they define the scale of the number and where the decimal point belongs. This is also widely used when working with the mnemonic display as well, but not only there. Next to the measurement button there is another one, red, which is marked write. And it activates the mode used to record the set point into the SKALA database. Well, how it was done? Well, typically process engineers would provide SKALA programmers with a special setpoint chart. And the programmer entered the request code on the left keyboard, then selected the type of setpoint and then used the right keyboard to enter its numeric value. Once again, this is only a small part of what the SKALA console can do. We will show you more of these functions in future episodes. But first we need to do a little bit more work. And now I have a question for you. So which SKALA function should we recreate next? Printed cartograms and tables, or a complete channel search programs for the MTK, or a more detailed simulation of reactor alarms and set points? So tell us in the comments. As usual, you can find bonus materials and project updates on our Patreon page. The link is in the description below. Thank you for watching, and we will see you in the next one.